Okay, this is Oscar, and today we're going to look at life cycle of star. Okay. So for stars, basically there are two kind of life cycles. One for bigger stars, and one for smaller stars. So the life cycle of both stars, both kind of stars, go under a more or less similar, um, similar progression. However, because of their size, there are going to be some minor differences in terms of the outcome. So we have let's start with smaller stars. Smaller stars, they are like all stars, they're formed with a bunch of space dust floating in space. And this bunch of space dust will attract more space dust because of the gravitational field that it holds. So once the space dust collects enough other space dust and it increases to a relative big size, it will compress until in the center, nuclear fusion occurs. Now, nuclear fusion occurs because at the center there is uh, it is hot enough and it is very high pressure. So this is what happens. And so in the center, nuclear fusion occurs. The star starts to become a protostar. So we go from a bunch of space dust to protostar. By the way, space dust is nebula. Okay, and now we have a protostar. And when nuclear fusion occurs, this protostar becomes a star, becomes a main sequence star. So main sequence star is basically like the main kind of stars in the main kind of stars in space. Okay, and so most stars will go through the main sequence, and then okay, it's basically the period where most stars spend their life on. And so basically, we go from uh, a bunch of space dust, which is nebula, and then the nebula attracts other space dust, which increases the mass. Increases the mass when there's a sufficient mass. There is a tendency for the center of the mass to attract other masses, and so basically the bunch of space dust compresses, and in the center there is this hot and dense environment. So this is what we call protostar, and then when the in the center, the core of the star, of this protostar becomes sufficiently hot and dense for hydrogen nuclear fusion, this protostar becomes a main sequence star. And so the main sequence star basically does nuclear fusion, and there's basically two things happening at the same time. So one thing is you got the compression force of gravity. Gravity always tries to compress everything to the center and to basically to attract everything as well. Right? This is kind of common sense because of the notion of black hole, right? Black hole is basically a very condensed mass that attracts that has an extreme force on everything near it. So it tries to attract everything inside that black hole. And so basically this is kind of similar. Gravity tries to compress everything to a single point in the center. But the thing is, when you see a star most of the time, the star remains at the same size, right? So that means not only gravity is acting on the star, there's some kind of other forces which balances out the compressing force of gravity in the star. Okay, and so what is it? It is the force generated from nuclear fusion. So nuclear fusion creates this massive amount of energy, and this energy is expressed in terms of increased temperature. This temperature kind of increases the average kinetic energy of the gases, which increases the pressure inside the gases, the pressure of the gases, and so the pressure of the gas kind of create an expanding force against the compressing force of gravity. And so basically these two forces balance out for the star to remain the same size. When the gravity is bigger, gravity will compress the star, and this will increase the pressure, which increases the inside expanding force. So you got that kind of self-adjusting equilibrium going on. And so this is what happens in the main sequence stage. And so of course, in the main sequence stage, you require nuclear fusion to kind of maintain that expanding force, right? But nuclear fusion, you kind of need fuels. You need these hydrogen atoms to collide with each other. And after they collide with each other, they generate energy and they form into helium, right? But so in this case, you don't have infinite hydrogen atoms. So eventually, at the end of the lifetime of a star, what happens is that it will run out of hydrogen fuel. But this running out of hydrogen fuel is not immediate. So you don't go from like full power to suddenly no power. Just like when you run out of fuel in a car, you don't go from 100 kilometers per second to 100 kilometers per hour to suddenly a stop, right? There is this gradual process of slowing down. Okay, so what happens is now as the star is running out of hydrogen fuel at the end of its lifetime, the expanding force is suddenly insufficient to cancel out the gravitational compressing force at the previous size of the star. So what happens now is then the gravity having a net force, having an overall net force, will try to compress the star to a smaller size. So our main sequence star at the end of its life cycle will try to compress. And so when it compresses enough, there is an increased temperature and increased pressure inside the core of that of the star, right? Okay, well, now we got an increase in temperature and increase in pressure. What this will do is that this will create a condition for harder nuclear fusions, such as helium. So what happens now is suddenly, when you compress to a certain point, you get nuclear fusion from helium that suddenly that releases a great amount of energy, a great amount of expanding force, overcoming the compressing force of gravity. And this will cause the star to expand. So now we have a seemingly much larger star, which we call it a red giant. And of course, right, like hydrogen atoms, there is limited hydrogen fields inside a star. There is limited helium inside a star. So this helium nuclear fusion will not continue permanently. At the end of its life cycle, again, it will run out of fuel. But when it runs out of fuel, now the star suddenly didn't. The star is small in this case, so it's unable to compress uh into a case where inside the core there is sufficient temperature and pressure for the star uh to 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 initiate a more difficult nuclear fusion. So in this case, what happened is that the star will explode. Okay, and so it explode in a it's kind of my metaphor for explosion. So what happens actually is that after it reaches the end of the red giant stage, it will do something like planetary nebula. So what happens is that um, all of the outside of the red giant is released from the gravitational pull of the star, and only a core of the red giant remains, and so that core is what we call uh, a white dwarf. This white dwarf, it is actually a dead star already because there is no nuclear fusion going on inside it. It is only uh, it is only bright because it is only bright because it is hot, but um, there is no continuous generation of power inside the white dwarf. And so gradually over time, it will become dimmer and dimmer and dimmer until it loses all of its temperature and it becomes a black dwarf, which is kind of unobservable in the universe. So this is what happens for uh, small star. And for big star, things happen kind of similarly, but there are a couple of key differences, right? So big stars, like small stars, they have something like they're formed because of this big bunch of space dust compressing for nuclear fusion, right? And then all of the pro-star stages are the same, and the main sequence star stages are the same. But it is a little bit different for the end of the life, at the end of the main sequence star stage for big stars. So what happens is, so for small stars, end of main main sequence stage would mean, um, you know, the uh, the mass compresses, so all of the hydrogen fuel runs out, mass compresses into a mass compresses to a point where at the center there is sufficient temperature and pressure, and that creates sufficient condition for helium nuclear fusion to occur, and that expands into a red giant. But the thing is, and then helium runs out, right? And then there is insufficient condition to initiate harder nuclear fusion. So what happens is everything just explodes. However, in this case, after the helium nuclear fusion, helium nuclear fuel runs out, the star can continue compressing until it is the condition to initiate harder nuclear fusions, such as lithium, and you go along the line, all the way up until iron, which is the atom with the highest binding energy. You can't initiate nuclear fusion after that. Well, you can initiate nuclear fusion after that, but you can't generate energy from initiating nuclear fusion for bigger atoms than iron. So basically, this is what happens, and so the star becomes, instead of a red giant, it becomes much larger, but it becomes a red supergiant. So much larger red supergiant. At the end of the life cycle, of course, you would imagine, since it is bigger, the explosion will be bigger. And so what happens is that the explosion becomes a supernova. And so it's going to be super bright in space. And what's left of the explosion is going to be the core. And the core is no longer going to be a white dwarf, because of the fact that the mass is the mass of the big stars are so big. The center of the core is much more condensed than the core of a small star. So what happens is that it overcomes something that we call neutron degeneracy pressure, and it becomes either a neutron star or a black hole. And so basically, this is the entire life cycle of the star.